Good evening, everyone. My name is William Lake. I'm a grad student in UCLA's astronomy program, and today we're going to be hearing from Dr. Guido Roberts Borsani and Tony Paul, who are also at UCLA. We're going to be hearing from each of them for 20 minutes, and then for each of them, we'll have a 5-minute question period for any questions that you have. So feel free throughout the talk to ask any questions you might have in the chat, and we'll make sure that they're answered. After the talks, we'll have a 10-minute trivia where there will be about 30 seconds per question. And we'll go through each question twice. And I'll talk more about that at that time. So feel free to stick around after the talks for trivia. So if we'll get started, we're first going to hear from Dr. Guido Roberts Borsani. He's a postdoc at UCLA. Guido graduated with a PhD in astrophysics from the University College London in 2019. He subsequently moved to UCLA to become a postdoctoral researcher working with Professor Tommaso Treu, studying the detection and characterization techniques of the most distant galaxies with the ground and space-based observatories, such as Hubble, Spitzer, JWST, and the Keck telescopes. When not searching for galaxies, Guido can be found searching for waves to surf, landscapes to explore, or new sports to try out. And you can take it away whenever you're ready, Guido.
Okay, let me just share my screen. Great. Well, first of all, I'd like to take the opportunity to thank the organizers for giving me the chance to give this talk. I've been wanting to do an Astronomy on Tap for a long time, so it's really nice to get this opportunity to do so. So without further ado, tonight I'm going to take you right to the very edge of the observable universe. And together we're going to go on a journey throughout cosmic time and discover how we found some of the most distant galaxies that we know of and why they played such a crucial role in shaping the universe as we see it today. So if we take our observations and our simulations of the universe as it looks today, and we take a snapshot of it at very, very large distances, it might look something like this. This is what we think it might look like. You see this wonderful sort of intricate web with this filamentary structure, which is actually composed of galaxies and galaxy clusters. And if we zoom in slightly to one of these nodes, let's call them, this is what we call the cosmic web, given it resembles arguably the most beautiful spider web you've ever seen. And if we zoom in, this is what it might look like. Over here on the left, you see one zoom in where you see a cluster of galaxies. If we zoom into that even further, you can see this clear filamentary structure with a central galaxy right there in the middle and lots of smaller galaxies around it. And then we zoom in once more and you can really see this bright, very central galaxy with all of its little neighbors around. And this is how we think the universe is structured as we see it today. If we want a slightly more realistic image, or one taken with our telescopes, an actual galaxy might look something like this. Again, you see this sort of wonderful structure, spirally structure, lots of stars, lots of gas, lots of dust. However, both galaxies and the universe didn't look like this throughout the whole of cosmic time. In fact, the universe in particular had quite a few phases, each with its own unique characteristics. So this is a little timeline, if you want, of the history of the universe. On the top right, you have the Big Bang. Most of you will know that the universe started with a Big Bang, after which it was so hot over there. It was really a soup of radiation and particles, too hot in the universe to form any sort of structure. This is right at the beginning of cosmic time. However, the universe underwent a very rapid period of expansion where during its expansion, it cooled. And this expanding and cooling allowed protons and electrons to combine and to form hydrogen. Most of us are familiar with hydrogen, the most basic element in the periodic table. And that's what we see over here, this sort of pink gas, if you want. That's what we call neutral hydrogen that filled the universe after the Big Bang. And after the forming of this hydrogen, we had a period which we call the Dark Ages. There are no sources in the universe. There are no stars, no galaxies yet that have formed. So there's an absence of light. However, gravity took control of the situation, let's say, and caused all of this hydrogen to collapse on itself and become hotter and hotter until the very first stars and very first galaxies formed around 400 million years after the Big Bang. So all of this in a split second, we've gone from the Big Bang to the Dark Ages to this period when the very first stars and very first galaxies formed. Now, these very first stars and galaxies emitted a ton of UV light, very harsh radiation. We protect ourselves from UV light on Earth. We're not so fortunate in the middle of space. And this UV light cleared out the hydrogen. It did what we call ionized the hydrogen. It essentially burned it, let's say. And this is a crucial period in the universe then, which we call cosmic reionization. And as you can see, as we continue along this timeline, these galaxies, which you can see, start becoming larger and larger. They start developing more and more structure. They start clustering together. And then you arrive finally to the universe as we know it, 13.7 billion years after the Big Bang, where you see all these beautiful galaxies with lovely structure, and we can observe these with the Hubble Space Telescope. However, as mentioned, there was this period called reionization, and this is an extremely important change in the composition of the universe. It was the last phase change of the universe up until what we see today. And because we suspect the first galaxies had something to do with this, we want to study those first galaxies. We want to find them on the sky with our powerful telescopes, and we want to study them. If we take a more realistic picture of reionization, we can take a slice of the universe, let's say, at that period of time and see how galaxies might have shaped it. So what you're going to see is a little video where you see dark clouds. Basically, these dark clouds are that hydrogen fog. And within those, you have galaxies emitting UV light, and they're burning that fog. And so all of a sudden, then, this is 13.5 billion years of cosmic history. You can see that these galaxies burned through the hydrogen to get this beautiful, transparent, and structured universe that we see today. So we really want to understand these sources. And to do so, we try to find them with our telescopes, which essentially are these wonderful time machines. So when you go out and you look at the sun, the light that comes from the sun didn't arrive here instantaneously. It took some time to arrive to Earth. In fact, because light travels at a speed of 300,000 kilometers per second, that crossing the distance from the sun to Earth takes about 8 minutes. If we go a little further out to the outskirts of our solar system, it takes a little bit longer, just over an hour or so. How about we go to the nearest star that we know of, Alpha Centauri or Proxima Centauri? That takes about 4 years for light to get from the star to us. If instead we look, for instance, at the center of our galaxy, of the Milky Way, the light that came from that center took approximately 26,000 years to arrive to us. And now that sounds like a lot of time, but in fact, it's minuscule amount of time, or it's a minuscule distance when talking or when comparing to the timescales of the universe. So if we take this one step further, you can see Andromeda, the Andromeda galaxy over here at the top. This is our nearest neighbor to the Milky Way. The light from that galaxy to arrive to Earth takes something like 2.5 million years to get there. If we go even further out to a cluster of galaxies that we may want to study, that light takes roughly 2.3 billion years to get there. So we're really increasing that timescale. And if we want to go all the way back, over here at the bottom, you can see this imprint by the Big Bang called the cosmic microwave background. It's the very first signature of the Big Bang. And that took 13.8 billion years to arrive to Earth. However, there is quite a distance between the clusters that we study here in the local universe and the very first imprint of the Big Bang. And that's the light from the very first galaxies. But we don't know what those galaxies look like or how far they are, where the first galaxies are. And so we don't know exactly how long the light takes to arrive to us. So given we're talking about light from galaxies, does the light from all celestial objects look the same? And the answer is no, it looks quite different actually. A galaxy is composed of very different components. You have stars, both young and old. Here you can see at the bottom, this bluish smudge is young stars, whilst you have older stars here, it's sort of in orange. You then have these kind of brown smudges over here all along the spiral arms. This is actually cosmic dust formed by supernovae. And then you also have gas in between the stars and the dust, gas from hydrogen, for instance, or heavier elements like carbon and oxygen. And all of these have an influence on the light profile of a galaxy. So do supermassive black holes. These are typically found at the center of most galaxies. So if we were to take the entire light profile of a galaxy and look at what that might look like, it could look something like this. So what you're seeing over here is the intensity of light as a function of frequency, and all of these different aspects have some impact on the shape of this light profile. So this is brightness as a function of frequency that you look at. But what you might notice is this characteristic drop in the intensity of the galaxy, and I'll tell you exactly why that is. Just for comparison, this is what the light profile of a star might look like. So you can really see, depending on which object you're looking at, the light profile might look very different. So this drop in intensity is extremely important because this is what we see when we look for galaxies in this neutral fog of hydrogen very far away. And the reason that you see this is because it's like looking for headlights on a freeway in fog. It's very difficult to see, and that fog diminishes the brightness of that light. And that's exactly what you see here. And this drop in brightness happens at a very specific frequency. We know where to look for this frequency. However, depending on the distance of that galaxy, this frequency gets shifted. There's a concept that we call redshift. So if you look at a galaxy over here and you look at Earth, the galaxy emits a certain amount of light. But because the universe is expanding still, as we know it, it's stretching that light. So you can see that as the galaxy ends up being further and further away, that light is getting stretched from perhaps the UV to the infrared. It's now at different energies or different frequencies. And so when we look for distant galaxies, our first instincts might be to look for them in visible light. But because of this stretching of the light wave to infrared wavelengths, most galaxies at very, very large distances will be found in the infrared, not in the visible. So the infrared is where we look for these ultra-distant galaxies. And in doing so, we've developed somewhat of a technique. If we remember this characteristic drop in the brightness of galaxies, this is what you're seeing over here in the top panel. If you ignore the colored curves, you can see a similar sort of light profile that we saw before, right? This is just the brightness of a galaxy as a function of frequency. And because we know where that drop in light occurs, and we've seen that it gets redshifted or it gets stretched to infrared wavelengths, we can predict roughly what the distance is, because this drop will shift as a function of distance. So the farther away a galaxy, the more that drop will occur to the right of this plot. And that means when we take pretty images of a galaxy with our telescopes, it means we're going to see nothing on the left of that drop where there's no brightness, but we're going to see something on the right where there is that brightness, where the galaxy is emitting light. And that tells us something about the distance. So if you look at these pretty images all the way now, we see that this drop in flux occurs roughly at this image over here, these two last images. And that tells us that this galaxy is extremely distant. So we can then use Hubble to take these exquisite images. Hubble is our premier and flagship telescope, or our premier time machine, let's say, launched into space in 1990, and it's been taking stunning images of the universe ever since. In 2002, it had a camera installed called the Advanced Camera for Surveys, or ACS, and this was a premier visible camera. where we can find a lot of distant galaxies as well. And in 2004, what happened was they took Hubble with the Advanced Camera for Surveys and looked at a random blank patch of the sky. And this patch of the sky is so small that if you were to take a pen and put it at arm's reach, the area of the sky would only be the very tip of that pen. And they looked for about 4 days, and this is what came out of this blank patch of the sky. This is called the Hubble Ultra Deep Field. It's one of the most exquisite images we've ever taken of the universe. It comprises almost every single object in this image is a galaxy. There are about 10,000 of them. This comprises about 100 hours of integration time on the sky, or if you want that in days, it's about 4 days of looking at the sky continuously. And a team of astronomers went out to look for the most distant galaxies in this picture, using the technique that we've just looked at. So trying to see where this galaxy drops out of the images to try and infer its distance. And these are the galaxies that they found. They don't look particularly special, but these are very, very distant galaxies. You can see they're extremely small, very faint, some of them very faint, some of them very bright. They're some of the earliest galaxies we know of. We're looking at galaxies when the universe was only about 1 billion years old. So this is one of the most successful images that we've had so far with Hubble. However, then in 2009, Hubble then got a new camera called the Wide Field Camera 3. What was special about this camera is that it started looking in the infrared, where most of the galaxies that we look for, the very, very distant ones, emit the majority of their light. So we took advantage of this camera and we tried to look at a patch of sky that was much larger than the Hubble Ultra Deep Field. This is one part of that image. This is called the Candles Survey. And if you were to compare all of the area with the moon, for instance, this is what it would look like. So every single strip you see here is part of this survey. And this is the moon to scale to give you an idea just of how small these patches of sky are. And we went about scouring through these images to try and look for the most distant and most luminous galaxies we could find. And lo and behold, we found 4. These are 4 of the most distant galaxies we know of. We inferred their distances with this dropout technique out of the images. And then we used the Keck telescope on Mauna Kea in Hawaii to try and confirm those distances, these 2 beautiful twin telescopes. And the telescopes confirmed the distances to those galaxies, making them the most distant galaxies we know of. These 2 galaxies, you see their light as the universe was when it was only about 500 and 600 million years old, or 4% of its present age. So we're really pushing back the frontier of what we can observe in terms of looking for distant galaxies. However, are these the most distant galaxies we know of yet? They were at the time, but they're not anymore. So I mentioned that this new camera got installed in 2009 on the Hubble Space Telescope, and this allowed us to look even further into the infrared, where most of these galaxies are emitting their light, and most of these galaxies are found. And so another team of astronomers went off and they combined the Hubble Ultra Deep Field, the optical visible images that were taken with that beautiful camera, and added the infrared information to this to try and look even further back into time and find even more distant galaxies. And this is called the Hubble Extreme Deep Field. In this image, again, almost every single one of these sources is a galaxy. There are about 5,500 of them. This image in total comprises almost 2,000 exposures, or roughly 500 hours of exposure time. That equates to about 21 days. So imagine taking your camera or your smartphone in space and leaving the shutter open for 21 days, and this is what you would get. And so the astronomers went, the group of astronomers looked in this image for the most distant galaxies they could find. So this is to give you an idea of the scale of the image as well. If you have the moon, again over here, and this is the patch of sky that they're looking at. So still a minuscule patch of sky compared to everything we can observe. So these observers went out, looked for the most distant galaxies they could find, and found 4 candidates that you can see over here. And one of these candidates happens to be one of the most distant galaxies we know of. That's this one here. Now, this galaxy, we pinpoint its distance so that we see its light as the universe was only 400 million years after the Big Bang. It has a bit of a funny name, GNZ11, but this is the most distant galaxy we know of yet. Only 3 or 4% of the universe's present age, and Hubble's really pushing through roughly 96% of cosmic time to see this galaxy. However, is this one of the first galaxies? The answer is probably not. Simulations and observations tell us there are probably sources farther than this. And we want to study those properties. This is what a galaxy might look like, one of the first ones. It might have a very small size compared to the Milky Way. It might have young stars that you can see in blue in this image. It might have old stars that you can see exploding. It can also have some dust in there. It can also have black holes, but we really don't know because the Hubble Space Telescope has reached its limits of what it can do. And we really need an infrared observatory, given infrared is where most of the distant galaxies emit the majority of their light. And so decades ago, plans were made to design and launch the James Webb Space Telescope. Now, the James Webb Space Telescope, or JWST, will be the successor to the Hubble Space Telescope. It is going to push further and further into the infrared than ever before, take the most exquisite images we're ever going to see in the infrared. It's comprised of this sort of gold-looking mirror, which is 18 different segments, each about 1.3 meters in diameter, weighing about 20 kilograms and made of beryllium. Each of these mirrors is covered with a very, very thin layer of gold. And you can see over here, there's also this wonderful heat shield. Because James Webb is going to be an infrared telescope, we need to shield all of its instruments from the sun. And so it has 5 different layers to protect its instruments from the heat of the sun. And it's going to be launched from French Guiana on an Ariane 5 rocket on the 22nd of December this year. It's going to take 30 days. So it's going to be all folded up when it goes into the rocket. It's going to take 30 days to arrive to its destination, within which that time it's going to unfold itself and get ready to take observations of the night sky. In total, it'll take about 6 months of commissioning before the telescope is ready to take observations, and we're really excited for it. Just to compare, I think I'm running out of time soon, but in astronomy, especially when you're dealing with telescopes, bigger is better. And over here, you can see a comparison with the mirror from Hubble over here, which has a diameter of 2.4 meters. And that of the James Webb, which is about 6.5 meters. So you have roughly 6 times more collecting area. And the entire telescope is about the size of an entire tennis court. So it is huge. Just to highlight what we might see. So you can see this is a visible image of the pillars of creation, a nebula in our Milky Way, the Eagle Nebula. And you can see lots of dust and some stars. But again, if you look in the infrared, where a lot of galaxies emit their light, this is what you see. And this is taken with the Hubble Space Telescope. And all of a sudden, you see this nursery of stars being born, and you see through the dust. And so it just highlights why we need the infrared as much as we need the visible. And so this is a comparison of what Hubble and James Webb might see. On Hubble, you can see the resolution is somewhat poor of this galaxy. But with JWST, we're going to be able to resolve this wonderful structure and try and determine the characteristics of the first stars and first galaxies. And whilst this talk was on distant galaxies, James Webb is also geared towards characterizing distant worlds. And so it's going to look at the atmospheres of distant worlds and try and understand the composition that is there behind it, to try and understand whether we might see signs of life. And so I'm going to end there, but this is an extremely exciting time to be involved in astronomy and to try and pinpoint the timing of when the first stars and first galaxies were born, and understanding the timing of cosmic dawn. So I'll leave it there, and I'll take any questions. Thank you.
Thanks, Guido. That was great. I think we do have some questions. So I guess to start out, why do you mentioned that JWST needs to fly for 30 days? Why does it need to fly so long when Hubble was pretty close to Earth?
Yeah, that's a great question. So Hubble was launched to what we call low Earth orbit. It's about roughly, I think, 150 kilometers in altitude above the Earth. And it was fine there. However, James Webb is an infrared telescope, so we need to protect it from pretty much, as much light as we can. And that means shielding it also from Earth's light. And so we're sending it further away to a point which we call the Lagrange point 2. And the Lagrange points are these points in our solar system where multiple bodies, so let's say the sun and the Earth, for instance, their gravity interact so that there's no net pull. And so the telescope can stay in that point without being pulled around by gravity, and it's far enough away from the Earth and protected from the sun that that it doesn't get heated up. So it's a matter of cooling it, really.
All right. Another question, and just in case anyone's not aware, you can ask any questions you have in the live chat on YouTube. Another question, what happened to the hydrogen that was ionized or burned in the reionization period?
Yeah, that's a great question. So hydrogen is just one proton and one electron. And so the UV light of these galaxies rips that apart. And so basically all that happened was we had this fog, and the galaxies stripped that fog apart. And so we essentially got clean air, let's call it. And Tony's going to explain this quite well in the next talk. But essentially that fog was burned away, and it's like going from fog on a freeway to clear air. And so that's what we see now in the universe. We don't see any more, or we hardly see any of this fog left because the galaxies burnt it all away.
All right. Another question. Why does JWST have gold on the mirrors?
So let's get back to that. Oh, whoops. JWST has gold on the mirrors because gold is, I think, particularly good at reflecting off some of the infrared sunlight from the sun. So it's just an additional coating. It's very, very small. It's, I think, less than a millimeter, just to give this sort of added layer of protection to reflect sunlight off.
All right. And then how does the distance an object is from us tell us its age?
That's a really good question. So so the distance we measure as a function of redshift. Redshift is this proxy for distance, and it's really what it tells you is the stretching of the universe. And because we know the universe stretched by a certain amount at certain times, if we can pinpoint the distance of the galaxy, a particular redshift, that tells us how much the universe has expanded throughout that time. So this is based mainly on observations, but backed up by our modeling of the universe as we know it. So the modeling tells us what we suspect we know, and then the observations confirm it in that way.
All right. And I think that might be all we have time for. Thanks so much, Guido. This was a great talk.
No problem. Pleasure. Thank you for having me.
Mm-hmm. And let's go ahead and let's set up for the second talk. All right. So next we're going to hear from Tony Paul. Tony is a fifth-year PhD candidate at UCLA. He works with Professor Alice Shapley. He studies galaxy evolution and can often be found remotely observing with the Keck telescopes in Hawaii until the wee hours of the morning. It's all you, Tony.
Amazing. Thanks so much for that introduction, William. And yeah, thanks again to the organizers for allowing me to give a talk this evening. I'm very excited. And thanks also to Guido. That was an amazing talk. And it really sets up really well my talk, which is also about a lot of the same questions we have about the universe's evolution. Just looking at it through slightly different ways. So not looking at the most distant galaxies, but looking at other galaxies. And I'm especially excited that people had questions about this ultraviolet light that occurs in the galaxy, because I'll really get into why that's important and what that does. Right, so let's just get right into it. So I guess the first kind of big picture overview here is, what is the universe made of? So here's some beautiful images here on the screen of what the universe looks like today. So these are, as you might guess from our last talk, these are galaxies. And galaxies are made up of a lot of different things. They're primarily made of stars. So most of the light you can see from these images are from the starlight within galaxies. Galaxies are large collections of stars, but also within galaxies, there's gas in between stars. Gas is also the fuel for stars. So there's plenty of that lying around. There are black holes. Just like our galaxy has a supermassive black hole at the center of our galaxy, most galaxies today have supermassive black holes at their centers. There's also dark matter, which we don't really know what it is, but we know that galaxies have a lot of it. I won't get too much into that. But yeah, these are kind of the basic building blocks of galaxies as we know them. So galaxies today, like galaxies like our Milky Way, they didn't look like they do now in the early universe. So this is just some quick snapshots of how galaxies have changed over cosmic time. So here in this image here, you can see galaxies getting closer to those really distant galaxies Guido was talking about, 10 billion years old, these galaxies. This is what galaxies like our Milky Way might have looked like back then. And over cosmic time, these galaxies change, they form more stars, the stars get older, and we come to these images that are more familiar to us in the bottom left panel here of galaxies like the Milky Way themselves. So galaxies have changed a ton over the universe's history. So the universe is also made of gas. So here is an image of Andromeda galaxy in the upper left. So this is the nearest neighbor, the largest Milky Way-sized galaxy that's the closest to us in the universe, as well as a smaller galaxy in the lower left nearby it. And here is actually a direct image of some ionized hydrogen, so some gas in between these two galaxies that the scientists that took this image were looking for. So sitting between galaxies today, there's ever present is this ionized hydrogen in between galaxies, which makes up the gas that lies in between galaxies. So there's not all empty space in between stars. So just like galaxies, the gas in our universe hasn't looked the same today as it did before. So before I get into that, I just want to explain briefly what ionized hydrogen is. So I think Guido referenced it in our talk, but in his talk, but I want to talk just very briefly, promise is the only chemistry in this talk, talk about what ionized hydrogen is. So here on the left is a picture of a hydrogen atom, which you may be familiar with. It's made of two atomic particles. There's a proton in the center, and there's an electron orbiting around that nucleus. This is a hydrogen atom. We can call it a neutral hydrogen atom here on the left. So on the right is an image of an ionized hydrogen atom. So in this scenario, the electron has separated from the proton entirely, and those two atomic particles are whizzing around completely independently. So the electron's no longer orbiting around that proton. So what causes this ionization? So what causes this ionization is high energy light. So here the wavy line you can see on the panel on the left is a piece of ultraviolet light hitting an electron that's part of a neutral hydrogen atom on the left. And after it hits this electron, it has enough energy to knock it away from the proton to cause this ionization. So ultraviolet light, as Guido was mentioning, is you can find it. It comes from the sun. The sun emits small amounts of ultraviolet light, and that's the kind of light that gives you sunburn on Earth. So it's that high energy light that is damaging your cells here on Earth. And it's also damaging these hydrogen atoms in between galaxies in the universe. So I mentioned that today the gas is ionized between galaxies, but the gas in the early universe doesn't look like the gas between galaxies today. So I really like this animation, so I'm going to play it again. This is also in Guido's talk. This is basically showing how the gas in the universe has changed over the universe's history. So here in the black, you can see that neutral hydrogen. So in the black is the electrons are orbiting around the protons, and in these kind of bubbles that are appearing are the bubbles of ionized gas being created. Yeah, I think this is a really, really fantastic simulation here. So yeah, this is a simulation. So it's made through a computer program with very specific models and using a supercomputer to generate this. So this is our best guess of what's happening in the early universe. Yeah, so to take this image or this video that Guido also shared into more of a clearer timeline here, here we can see the universe's history all in one line, in one picture. So here on the far left, we have the Big Bang, which is about 13.8 billion years ago. And on the far right, we have today. So these earliest galaxies that Guido has been diligently looking for are around here, about 500, 700 million years at the Big Bang. So after these galaxies form, they're forming stars, they're interacting with each other, they eventually reach these beautiful spiral structures we see today on the far right. So while these galaxies are changing, again, the gas has also changed. So here on the left in the blue is that neutral hydrogen, the proton electron together. On the right is the ionized hydrogen, then broken apart. So where does ultraviolet light come from? So we need ultraviolet light to make this transition in the gas in between galaxies in the universe. We need ultraviolet light to make that happen. So as I mentioned, ultraviolet light comes from our sun in small amounts, but really the dominant sources of ultraviolet light in the universe are really, really massive stars. So these stars are 10 to 100 times larger than our sun. Here's an artist's rendition of one of these massive stars in the lower left. And because these are so large and there's so much fusion going on in these stars, they're emitting a ton of really high energy light. And these are really primary sources of ultraviolet light in the universe. And you can find them in these stellar nurseries. Here's an image of one in the center. Wherever you see stars being formed, you're going to find these very large, short-lived, high energy sources. So another astronomical source that emits high energy ultraviolet light are black holes, and specifically active black holes with very intensely radiating regions around them, the infalling material becoming super, super hot and emitting high energy and ionizing light. So if our planet Earth was closer to one of these black hole systems, it'd be very bad news for our skin. We would immediately get skin cancer. So not very hospitable to humans. So this is where ultraviolet light comes from. So we want to know, can we see this ultraviolet light that is driving this change in the universe's composition? Can we see it from these galaxies? So this is this idea of whether we can see them or not definitely is definitely part of what Guido was discussing in terms of that dropout technique. So just to borrow his analogy here, you're trying to see headlights through a dense fog, basically. So the headlights here are the ultraviolet light from a galaxy, and the car is the galaxy itself. And you're across town, and you're trying to look at a car, very far away with tons of fog in between, and you're trying to see if the lights are on or not. The answer is you couldn't because the fog's there. So in this scenario, the neutral hydrogen is the fog. So that's the material that the ultraviolet light can't penetrate. And the ionized hydrogen is the clear air that the ultraviolet light can freely pass through. Right, so basically these galaxies that are actually driving this, ionization process in the reionization era, we can't see directly their ultraviolet signatures. We can't actually see the light that's making the universe change because it's basically too foggy back in the universe's history. So what a solution that my research specifically looks at is instead looking at the ultraviolet signature from galaxies once the universe has become transparent. So these galaxies are after the universe is mostly ionized, so after 1 billion to 2 billion years after the Big Bang. And we can see the ultraviolet signatures from these objects, so we want to study them. Yeah, so these galaxies are at what we call cosmic noon, as opposed to cosmic dawn, which is the beginning of galaxies. This is cosmic noon. So here are some images of these galaxies we want to study here. So as you can see, definitely not as beautiful as and high resolution as the galaxies in the universe today. But this is some of the best imagery we can get of these galaxies at cosmic noon. And we want to use these, we want to study them as ultraviolet suspects to see what's actually going on in the period of the universe that's opaque to us. So a little bit more about cosmic noon. So cosmic noon is named as such because basically it's very hot and very intense. So in this period of the universe's history, galaxies are forming a lot of their stars. There's a lot of fuel for galaxies to create stars. So it's very intense for star formation. It's also, galaxies are interacting with each other, they're merging, they're running into each other. It's a very chaotic time for the universe and galaxy evolution as a whole. So this specific time in the universe's history is a super interesting time to look at if you're interested in how galaxies change over time, because a lot is going on in this time period. So we want to study the ultraviolet signals from these galaxies. We want to know basically how much ultraviolet light, high energy light, is leaking out of these galaxies that could be, destroying that neutral hydrogen in the earlier part of the universe. So here's just a rendition of that ultraviolet light escaping from one of these galaxies at cosmic noon, traveling through this ionized hydrogen. As you can see, the protons and electrons are separate from each other. They're not blocking any of that light. And here on the right, it hits our telescopes. And we tried to study it and try to figure out how much ultraviolet light are coming from these galaxies. Yeah, so just to reiterate here, basically, because the ultraviolet light can travel to us in these galaxies, whereas a galaxy in the early part of the universe, when it's foggy, cannot, we can basically infer how much ultraviolet light is leaking from these galaxies using the information we get from galaxies later in the universe's history. That's really the crux of this type of study. So just a brief aside to talk about how we actually see this ultraviolet signal. We can basically see ultraviolet signals from galaxies by splitting the light from the galaxy into different colors or frequencies. So this white line here is the light traveling 10 billion light years to get to our telescopes. And within our telescopes, there's a system that acts kind of like a prism. And this prism splits the light into different frequencies, as you can see in this animation here. So here you can see all the visible colors, the colors of the visible spectrum. But far off to the blue side is the ultraviolet light. So that's higher energy that we can actually see. It's invisible, but with these telescopes, we can actually see this light directly if we split it up and look at the specific spot where this ultraviolet light is falling. So I wanted to show you guys kind of what kind of this data looks like from the telescopes themselves. So here in this kind of grainy looking image here is actually directly from the telescope itself. And this line is essentially the signal where going up and down the image is the frequency of the light. So you can see it's brighter in certain parts and dimmer in other parts. And a certain part of this is the ultraviolet part. That's the part we want to look at. So I also mentioned that this data was taken with the Keck telescopes on Mauna Kea in Hawaii, which, a lot of this really amazing sort of analysis is really contingent on data from these telescopes. Yeah, so again, some questions we can answer by looking at these galaxies at cosmic noon is, when does reionization actually happen? So because the universe is so foggy and opaque, we don't know exactly when this process is taking place. So, for example, 800 million years after the Big Bang is this process of reionization. Is the hydrogen almost evaporated, or is it just getting started? We can't tell because the ultraviolet light is invisible to us. But by looking at galaxies later in the universe's history, we can make inferences about what's going on in the earlier part of the universe's history. We can also answer questions like, is reionization actually caused by massive stars, or these extremely active black hole environments? So if we look at the galaxies at cosmic noon, and we see most of the radiation is coming from massive stars, the ultraviolet radiation is coming from massive stars as opposed to black holes, we can infer that in the earlier part of the universe, most of the radiation is coming from massive stars as opposed to active black holes. So this is the only part of the universe's history where we can answer these questions. Yeah, and I just wanted to kind of end my talk by saying, my research in later part of the universe's history is really complementary to studying the most distant galaxies that Guido was talking about. By studying my galaxies, our galaxies in cosmic noon in detail, and then making inferences with these incredible surveys to look for the most distant galaxies, we can really build a clear picture of how the universe is changing over time, and really pin down when and how reionization is happening. All right, so I want to thank everyone for sticking around, and the organizers again, and I can take any questions.
Thanks so much, Tony. That was a fantastic talk. And we do have questions for you. So let's start with where do the electrons go when hydrogen gets ionized?
Yeah, that's a great question. So the electrons, they don't go, they don't go very far. So basically the hydrogen, the protons, the electrons are still in kind of one cloud. Like if I were to show if I were to show that image from the directly ionized hydrogen image between Andromeda and another local nearby galaxy, basically that proton and electron soup is still together in various clouds between galaxies. So they don't necessarily get flung super far away, but it kind of becomes one from amorphous mass of protons and electrons together. They're just not orbiting each other. Great question.
All right. Yeah, and another one. So what causes this neutral hydrogen to act like fog when the ionized hydrogen is clear air? Does light interact with the two types differently, or what's going on there?
Yeah, that's a great question. It's a fantastic question. So basically, the reason it's fog is because when the light, ultraviolet light, hits the neutral hydrogen and causes the electron to get knocked off, that electron actually absorbs that light entirely. So it's taking the energy from the light itself and transmitting that energy into like the velocity to get it away from the proton. So that light is actually completely absorbed by this process. So that's exactly the reason it's a fog, is because whenever this ultraviolet light finds neutral hydrogen atom, the electron will absorb it and it will get separated and the light is gone. That's a great question.
And then another one, how do we use the light from cosmic noon, where ionization is mostly or fully complete, to infer information about ionization earlier in the universe?
Yeah, amazing question. So there's a lot of different ways we can do this, but one way, for example, is we could look at how much ultraviolet light is in these galaxies and compare it to light that we can actually observe in galaxies in the earliest parts of the universe. So we can build like proportions between ionized light and non-ionized light to basically see, okay, so say we see this much light in the visible in galaxies in the earliest part of the universe. And if we know the relationship between light in the visible to this high energy ultraviolet light in the later parts of the universe, we can basically work backwards to figure out how much is being emitted in the earliest universe. But it's definitely a very active part of research, and there's still a ton of open questions on how different properties of galaxies connect to how much ionizing light they're producing.
All right. And then another one. So you've talked about our cosmic history, and you've talked about how hydrogen combines and then gets ionized. But what does our cosmic future look like? So when stars die and presumably stop ionizing hydrogen, will we get neutral hydrogen again, or what will happen down the line?
Yeah, that's a great question. So yeah, ionized hydrogen can theoretically, it could recombine into neutral hydrogen, given enough time and given basically enough time for that gas to compactify. So it's definitely a process that happens. It's just extremely slow at this point. And so much of the universe is ionized, it would take a very long time for that to happen. But yeah, absolutely. Our cosmic future looks like, there's going to be fewer and fewer stars being made and fewer ionizing radiation being sent out into the universe. Compared to cosmic noon, the amount of young massive stars and active black holes in the current universe is way, way lower. So it's only going to get lower from here.
And another question, are there any theories on why reionization started? Were there not always massive stars?
Yeah, that's a great question. So this this question really ties into how do stars form in general. So, what conditions are necessary for stars to form? And some conditions that are necessary, basically the gas has to be dense enough and cool enough for it to compactify into a star. So in the earliest parts of the universe after the Big Bang, it's too hot and it's moving too fast for it to condense into stars. But the longer the universe goes on for, the more it expands, the more it cools down, and the more that gravity starts to compact this hydrogen gas, stars can form. So it takes some time, and it takes the universe expanding to get the conditions right for stars to form. But it's an amazing question.
All right, thanks. I think that's all our time. So thanks so much for a fantastic talk.
Thank you.
To both our speakers. So now we're going to go ahead and do trivia. So the way this is going to work is I'm going to put each question up. There are 8 questions. You can write your answers down wherever. And each question is going to be up for 20 to 30 seconds, and we'll go through each of them twice. At the end, you're welcome to email your answers to us for a chance at a prize. And yeah, and we'll also show the answers so that you can check yourself. There are 8 questions total. All right, now we're going to go through the questions one more time, just so everyone has a chance to make sure they've answered each one. All right, that's all the questions. So here are the answers. If you have 6 or more correct answers, please email us with a picture of them to be entered in a raffle for our prizes. And our email is here. Other than that, thanks once again to our presenters for 2 wonderful talks. And we'll see all of y'all next time. Have a good evening.